Hello guys, so this is a calculus part 2 and this is going to be about limits and derivatives. So last time we talked about limit. A limit is a value that a function, it could be a sequence as well, that approaches as the input approaches to a certain value. So for example here we have an equation limit a to 5 and a function a plus 5. What does this equal? A is going towards 5, so we replace a to 5 and 5 plus 5 equals 10. This is the limits. So we're going to be talking about calculus. This whole unit was about calculus. Why did we start with limits? How are limits related? So in calculus, there are mainly differentiation, which is also called as derivative, and there is an anti-differentiation, also known as integrals. We're going to be talking about derivatives and how it's related to limits right now. So derivatives. Derivatives is the instantaneous change of a function. That's the definition of a derivative. So let's talk about instantaneous change. Before that, let's talk about the average rate of change. So in this equation over here, what is the average rate of change in y over the average range of change in x? And the domain is limited to 0 to 2. So I'm guessing you guys have your answer. Let's check it. So the answer is change in y is from 4 to 0, because when x is equal to 0, it's 0, y is 0, and when x is equals to 2, y is 4. So 4 minus 0, and that's equal to 4. Change in x is 2 minus 0, the same way we did, and it's going to be 2. Now here, what you have to remember is that whenever you're looking for a difference, you have to do later minus before. Not so what I did was 4 minus 0, not 0 minus 4. But in math, because you're finding the difference, you can do 0 minus 4, but you have to keep your method constant. So if you did 0 minus 4, then you have to do 0 minus 2 as well. So going back to where we were, 4 divided by 2, because I asked for average rate of change in y over change in x. So 4 divided by 2, 4 is the change in y and 2 is the change in x, equals 2. So that's the average rate of change in this function from 0 to 2. That's the conclusion. The equation changes in average 2 in domain 0 to 2. Then, how about instantly at a certain point? What's the instant? Instantly, how much does it change? So let's say we're trying to find the instant rate, change of rate at the point 1 in this function. Oh, by the way, this function is a really simple function, y equals x squared, this whole graph, just to help you guys. So this is where the limits enter. So we measure the average by getting the difference from x and y from 0 to 2, and that's how the slope would look like from 0 to 2. So now let's make the domain even smaller. So we're making the domain from 0, let's say about 1.5. So we made the domain a bit more smaller. And now we've made it even more smaller. This looks like about 0.8 to 1.5. And even smaller. We're making the upper and the lower domains even smaller and smaller. And if we continue doing this, the domains are going to be somewhat really close to 1. So now let's extend this line without changing the slope. So we're just going to make it longer so we can see how it exactly looks like, because this is way too tiny for us right now. So this is how our extended line looks like. And so from now here, so congratulations, we have found what the change of rate of the function at the point 1 is. And if you see here, it's from 0.5 to 1, and the y is going to be 0 to 1. So 1 over 0.5 is going to be 2. So the slope is 2. So our change of rate is 2 again. Interesting. So did you find the connection between a derivative and the limits? We limited the domain smaller and smaller until the two domains had a difference of 0. So we made it super close to 1. So the upper domain could have been 1.01 and lower could be 0.99. And if you keep on doing that until the very limit, until the two domains are super close to 1, then their difference is going to be going towards 0 as well. But in math, as you know, 0 cannot be a denominator. 5 divided by 0, what is that? We don't know. It can't work. By setting the domains as the limits, the b minus a, as we set the b minus a as a limit that gets close to 0, but is not becoming a 0, we find the instantaneous rate, which is the derivatives. So I'll explain it one more time. You see here, this is a very tiny part, tiny part of the function y equals x squared, the one we just saw. As you see, as it's super close, you see that it looks like a line. It no longer looks like a slope. So we're repetitively continuing this process until we see the two domains very close to just the point 1, and that's where the limits enter. We're limiting the domain, and we're making our domain smaller so that we know that our slope, the instantaneous change of rate, is exactly at the point 1. That's why we are using limits and derivatives.